Welcome once more to Norvento's blog. This month we are dealing with a very interesting subject, nuclear fusion. To talk about it, we have invited Mr. Alberto Loarte, Head of Science Division at ITER Project. Welcome, Alberto, and thank you for joining us.
Hello, thank you.
Alberto, 2 years ago, you wrote a very interesting article for our blog on fusion energy and the ITER project. Our audience can still read it in our blog. However, for the newcomers, could you make a brief introduction on the ITER project, please?
Okay, so as I said, this is the ITER project, and this is a large installation. As you can see, this is a platform which is built, which is of the order of several tens, 40 to 60 hectares. And the project itself aims to reproduce on Earth the processes that lead to the production of energy in the universe. So, and this is the fusion of hydrogen, which take place in the stars. This nuclear reaction in which hydrogen is fused into helium and is a very effective way to produce energy. The first evidence that fusion took place in the stars was in the early 20s and 30s, and since the 50s, research started to try to reproduce this on Earth. Now, the way we reproduce this on Earth is using the fact that gases at very high temperatures lose the atomic nuclei, lose the electrons, and therefore they are charged electrically and can be controlled with magnetic fields. And ITER is based on a particular design which is called a Tokamak, which is a Russian name that means toroidal chamber with magnetic coils, because the shape of the plasma is the same of a donut. So what we do in practice in ITER is to fuse two types of hydrogen, heavy hydrogen. One is deuterium and the other is tritium. Deuterium is very abundant in the universe, and it was formed at the beginning of the universe itself during the Big Bang. Tritium is not naturally existing because it decays radioactively, and we produce it from in nuclear fusion reactor. It will be produced from lithium, which of course is very, very abundant. So as I said, these two nuclei fuse together. They form a helium atom, a helium nuclei, and a neutron. The neutron escapes the magnetic fields that we create and hits the wall of the reactor, and this is what is used for heating up water and producing electricity. In ITER, we will not do this because it's an experimental reactor. And the high energy helium nuclei actually stays in the gas, in the plasma, which we call plasma, this very hot gas, and gives the energy to the hydrogen, and so it self-heats. And this is what we want to reproduce in ITER. This is a very efficient process, and by fusing 1 gram of deuterium and tritium, we can get the same energy of 8 tons of oil. Now, of course, in ITER, we cannot reproduce the conditions of the stars, because the stars, of course, the hydrogen is the pressure of this gas is contained by the gravity. As I said, we use magnetic fields, and these are used for two purposes. One is to compensate the pressure of expansion, because this gas is very hot. By the way, in ITER, we will have gases which are 10 times hotter than the center of the sun. So we will operate at several hundred million of degrees. And we use these magnetic fields to reduce the losses of heat from this plasma, but also to compress it, because in ITER, these gases will have a pressure of several atmosphere, and the magnetic fields make a pressure on the gas. And for this, we use coils that I will describe later that create a current in this gas, a very large current, 15 megaamp, which is several million times higher than what we have at home in a socket. And also another field of several Tesla, which is several 100,000 times the field of the magnetic field of the Earth, to reduce the heat losses. So as such, ITER is this is the main core of the project. This is a Tokamak. It's a very large machine, as we will see later, which is now started to be assembled. And it has the idea is to achieve 500 megawatts of fusion power by heating the plasma, because of course we have to heat the gas first so that the fusion reactions can take place. And we will use for these 50 megawatts. So we have a net gain of a factor of 10. This is what we want to demonstrate in ITER. And by this, the idea is to demonstrate that fusion power can be used as an energy source for the humankind, both the scientific and the technological aspects. As a project, ITER, the first ITER design started actually in the late 80s and proceeded through the 90s, and finally in the 2000 the project was approved. The 2006 was approved for construction. Apart from the Tokamak, which is what I saw here, as you can see, there is a lot of infrastructure in the project, because these magnets, for instance, what we use to create the magnetic fields, have to operate at very low temperatures. So we have a very large cryo plant to cool them to minus 269 degrees Celsius, or 4 degrees above the absolute zero. And of course, we need a lot of current in these magnets. So we have a electricity supply, converters. We have here the heat rejection system, because as I said, we are not in ITER, we are not converting the steam we will produce basically in a reactor into electricity. And also there are specific facilities like this Cryostat workshop or this cold winding facility that I will mention these parts later, which are dedicated to fabricate some of the components in ITER which cannot be transported because they are very large. So you can see it's a very large, it's actually the largest scientific project at the moment under construction in the world. Yep.
Yeah, it's huge, really. Yeah.
It is huge, yes. It is very large. and of course this is a global challenge. And as I said, in 2006 it was approved the signature to construct the project was done. Since the project is based in France, the signature was done at the Presidential Palace in Paris. And the ITER members are shown below. So it's China, the European Union, India, Japan, Korea, Russia, and the USA. And these ITER members contribute to the ITER project with the funding, but also with the components that I will show later. And they represent more than 50% of the world population and 85% of the economic power, the gross national product. So it's really a world answer to the problem of energy supply.
Yeah. Thank you very much for the introduction. It was great, and I think our audience have the concepts clear now. And I think that the project made great progress in these 2 years. Back in 2019, when we first talked, the walls of the Tokamak building were still under construction. Last year, the first components manufactured all over the world were delivered to ITER. What were those parts, and which countries were involved in their manufacture?
Okay, so as you said, and I shown the photo I shown of the ITER site is of November last year. So you can see that here we have done a lot of progress. When we talked before, these buildings were not yet finished, and now you can see how much it has been done. At that time, practically only these 2 buildings that were finished, and the rest were under construction. So on the civil work, there has been a lot of progress, but also in the components, and this is what I am going to show here. So the first thing is that, as I said, ITER is a worldwide challenge, and there are the 7 ITER members that contribute to it. So here we can see a layout of the Tokamak at who does what. So the first thing, as I said, the whole Tokamak is kept at very low temperatures. The magnets are kept at very low temperature, and because of this, we need a thermal container that isolates from the exterior. This is what we call the Cryostat. This is being built by India, and this is one of the things that is being the parts are being sent to ITER, but they are being assembled on site in one of the buildings that I showed. Other parts are the connection to the coils, the superconducting coils. These are provided by China and are called feeders. Because you have to get to very low temperatures, there are several thermal shields that isolate the components from heat sources. These are called thermal shields. They are produced by by Korea, and I will show some of the examples of these thermal shields. Some of them are already installed. The bottom part here in red is already installed. And then there are the coils, one that produce the toroidal field coils. These are built, the coils themselves are built by Europe and Japan, but the cable for the coils is built by all ITER partners except India. You can see here the poloidal field coils, which are these round coils here and here and here. These are built mostly by Europe. The one at the bottom, which I will show, has been built in China under contract for Europe, and the one at the top is being built in Russia. And the vacuum vessel is being built by Europe and Korea. So this year, what we got mainly was then there are the in-vessel components. These are still in fabrication, and these are built by Europe, Korea, by Europe, Russia, and Japan, and also for the blanket modules from China and Korea. But these are all under construction. The ones we got this year, really, in the last 2 years, are the main components of the Tokamak. So this concerns coils, vacuum vessel, and of course the cryostat, because we need them to start assembly. The components that come later for inside the vacuum vessel, they will come in the next year. So I will go now in detail of the things that I will show. First, I will show a drawing so that you can see what I am going to show later as manufactured parts. Okay. So the first thing is, as I said, we got the first sector of the vacuum vessel. This double wall contained vessel is being built by Europe, Korea, and Russia. So we got the first sector from Korea this year. It weighs 8,500 tons total. So every sector weighs it's divided into 9. So every sector weighs 1/9 of this. And it has a volume of 1,400 cubic meters. The plasma in ITER, so this hot gas, which I mentioned before, will have about 840 cubic meters. For a comparison, the largest tokamak that I see so far has a volume about 10 times smaller, there are two tokamaks, which one is in the UK and the other in Japan with this volume. So this I will show the sector that we have received. Another thing that, as I said, we have received some of the coils already. So these are the toroidal field coils, which are shown here in yellow, that produce a field in the axis of the donut, and the poloidal field coils, which are in red. The bottom one has come from China, and the others are being fabricated on site at ITER. The upper one, which is this one, is being now finished in Russia. The central solenoid is manufactured in the US and will come soon. So you can see here that all these things, many of the components in ITER typically weigh several hundreds of tons. As an example, to give you an idea of the forces that interact in these magnets, this central solenoid magnet is kept by these green bars, which are steel bars that have very high strength, and two of them can hold a rocket to ground without taking off. So they have extreme strength. They are very, very, very high strength steel. It operates at very low temperatures. Now, the cryostat, as I said, is the vacuum vessel that contains everything. And this is built by India in parts and is put on site at ITER. You can see a person here, so you have an idea of the size of this. And this year, what I am going to show is the start of machine assembly consisted on the finishing of this and putting it on site. And now we have this part and this part also on site. Already in the Tokamak reactor building, these two parts this part is already manufactured and the top is being finished now. So this is something which has been very successful, completed actually in the last 2 years since we interacted last time. So one of the problems, of course, you will see many photos, is that these components come from all over the world, and the ITER site is of the order, let's say, of 80 kilometers inland. So they come by large boat to a main harbor near Marseille, and then they are brought by smaller boats to this place, Berletan, and then by road to ITER. And of course, some part they have to cross the motorway, because in the motorway there are bridges, and these parts are very large and they don't go. So this process takes many days. It's something that is done during the night mostly, and it is quite complicated. So every of these large component takes a while to arrive to ITER. It's not as simple. And the trucks, of course, that carry them are large and they go very slow. So you will see photos of these things now in the next slide. So for instance, here you have the toroidal field coils. This is the first manufactured coil, was made in Japan. You can see by Mitsubishi, was put together in the case. So this weighs of the order of 360 tons, and it was positioned inside this case with a 0.5 millimeter precision. One of the things which is very peculiar for ITER is that in order to get a very high magnetic field symmetry, the components have to be manufactured and installed to precisions of millimeters. So there are many industries that make very large components, but manufacturing to this high precision is technologically very challenging. So you can see here that the first coil that actually arrived in ITER, but these large trucks which I mentioned here, you can see here 6. The first coil was manufactured in Japan, but the first one that arrived was actually from Europe because they come from Venice, so they is much closer. And you can see how the coils have continuously arriving from last year in April until this year in March. So we have now 6 on site. In total, the machine has 18. So we have 1/3 and already here and one spare that will come later at the end. Now, the poloidal field coils are the ones that go in the axis of the donut. As I said, the poloidal field 6, which is the one that goes at the very bottom of the machine, was manufactured in China for the EU. And this is here at the ITER site undergoing test. This is the transport, you can see. So these are very large components. And the others, which are very large, have to be manufactured on site. And once they arrive, all the coils, or when they are completed manufacturing, there are a series of tests to be sure that the coil is well built. And here you see people very happy because they completed the test of the next coil above this one. This was completed earlier. And of course, manufacturing doesn't stop. So now they are building, and this is a photo of a few days ago, they are building the next coil up. So all this process is ongoing. We have 2 coils finished and tested, and we are continuing with the next ones. And this is all now very, very recent. The vacuum vessel, as I said, came from Korea last summer, and this is the vacuum vessel at the ITER site. So this is the first sector. You can see here the ITER staff doing controls. So you have to test that the vacuum vessel doesn't have any leak, and you have to test to measure it in detail, etc., because now it has to be assembled. So now we are, as I will show later, at the moment of starting to use this vacuum vessel sector for starting the assembly of the first sector of the machine. And the next big components that we have to do with the cables that bring the currents into the coils. These are the so-called feeders they made in China, and this is one that was installed in February. And these cables, you go from a copper conductor, basically a large copper conductor, to a superconducting element. So they are complicated and actually very large. You can see them here. Another thing that I mentioned is that we have, of course, received the thermal shield, which is this structure that prevents the heat from the vacuum vessel, which is kept at 100 degrees to go to the superconducting coils, which is kept at minus 269. This is silver plated, that is why it's so shiny. And you can see here the cooling channels to cool it so that you can keep the temperature down. Finally, we have the cryostat, which is the thing on which the machine is enclosed. And actually, as I will show later, this is the bottom of the cryostat, and the installation of this mark officially machine assembly. So as I said, we have installed this, we have installed the next part, and the one is done in 4 parts. So these 2 are installed, and as I will show later, the next upwards from this one is manufactured, and the last one, which is the top lead, is being finished now. This is a photo of a few days ago. Okay. So these are more or less all the big components that have arrived and that have allowed us to start machine assembly this year.
Yeah, you have started, I think it kicked off last July or something like that in an event. And how is the assembly of such large components carried out? How long will the assembly phase take?
Okay, so as I said, the assembly in fact started in May last year, but of course the official ceremony took place a bit later, and it started with the placing of this component, which is the bottom of the cryostat, into place. So I'm now going to show how this thing goes. Of course, these components are very large, so a key essential component is the use of these cranes, these large cranes that can take components of, this one weighs, I think, 1,250 tons. So they are very, very large components. So the use of cranes is essential for this. So I will show now the first to understand how the assembly is done. So this is the Tokamak building where the Tokamak will be placed finally. All assembly is done from the top. So there are cranes that come from the top of this building and they put the things on place. So you can see this is the view from the top of this building. So from up here, and you can see here that there is a base and there are many ports. These are the ports that connect the Tokamak to the various system to heat the plasma, to inject the deuterium and the tritium, to measure the plasma properties, to reprocess the fuel. That we have to eliminate the helium to reinject it in the tokamak. So this is done through all these holes, all these ports. These are the ports of the vacuum vessel. So all the assembly comes, as I said, from the top, and components are installed and welded and positioned. This is what we call the tokamak pit, which is let's say the reactor building itself. So the way it goes, as I mentioned, is this building starts here behind the crane, and components are in the assembly hall, which is a very large building in front of it, and they are taken by crane and drop from the top. On top of this, not all assembly takes place inside this tokamak building, but many components are put together in subsets in advance of putting them in the pit. And for this, we use these very large structures in gray that I will describe later in more detail. So here you see really the start of the assembly. We was the placing of this part, which is the bottom of the cryostat, onto these supports by a crane. And this was done in May last year, at the end of May, and then we have this discontinued by the next sector, and you can see how in this sector of the cryostat is dropped into the tokamak building, into the tokamak pit, and welded by robot. By the way, people are just the staff here is just actually checking that the robot is doing high welding. This is a very high quality welding because it is a vacuum component and you cannot have leaks. So we continue with this. And as I said, you have to insulate all these components from the heat. And for this, we install these so-called thermal seals. And actually, this is a photo of the installation of the thermal seal in January. So you can see all the components are built, put together in the assembly hall, and then move with cranes over this wall and then inserted in the tokamak pit, where they are welded, attached, etc. The sequence of the assembly itself. First, we have to put some supports on which the components are based, and this is what we are doing now. You can see a photo of a few weeks ago, a month ago or so, where we put all these supports to install the components, and then the components are being built on top of this. So this is already the way it is. So we have the bottom cryostat. Now we are setting the supports for the toroidal field coils, for the poloidal field coils, and then we will place the coils one after the other and assemble the machine starting from the bottom up. So this is the way we do the assembly. That is why it was very important to have the components, these two coils finished, the PF5 and the PF6, which I shown before, because these are the ones that go to the very bottom, and then you put the machine on the top. So if you don't have these coils, you cannot start the assembly of the magnets of the machine. And as I said, when you go into this tokamak pit, some of the components are pre-assembled. So one of the main things is to, of course, pre-assemble the vacuum vessel with the toroidal field coils. And for this, we have this subsector assembly tool. These are two, actually we have two. These are two very large structures where you put the vacuum vessel sector in the middle and you adjust the toroidal field coils by the sides. And you insert the thermal shield. So all these parts, as I said, weigh typically several hundred tons. So this is a very massive steel structure. And of course, before using it, what is what we are doing now, this was tested to be sure that they could handle and you could position the components to very high alignment precision. This machine was built in Korea by this company, and here you can see the test. This is with concrete structures to test that you can do what we are supposed to do now. This was a test a few months ago. So for instance, here you can see the positioning of the vacuum vessel sector. So the vacuum vessel sector, of course, is put in an horizontal position. It's an horizontal position. You have to be lifted and then move. And actually, this is something we are doing now. So this photo is of a few days ago. So you can see the vacuum vessel sector, and it will be taken by these cranes and then put here. We have already tried lighter components like this thermal shield, so you can see them put here. So now we are really starting the first assembly of the first sector. Once this is complete, it will be taken over this over the wall with the crane and will be installed in the Tokamak pit. And this is expected to the first completion of the sectoral movement is expected sometime in the autumn this year. So this is a very important moment for us to show that we can put 1/9 of the machine together with all this. As I said, all these things have precision accuracies of installation of in the millimeter range. So this is, although the parts are very large, the precision has to be very high. And this, of course, something which is a very difficult thing to achieve. So now is when we are demonstrated that the schemes that we have designed to do it actually work in practice.
Wow, that's amazing. And how long will it take this? Well, I'm sorry.
Yeah. So we expect to, okay, this of course is all a bit impacted by the COVID, as we will discuss later, but so there could be some months of delay compared to the present plan, but the idea was the plan is to finish and I will show this in more detail later, to finish the assembly towards the end of 2024 or the beginning of 2025, and then we have 1 year to check that all the components are properly working, etc., before we do the first demonstration. So we have about, let's say, 3.5, 4 years from now, more or less.
And as you said, how have you been dealing with the COVID-19 pandemic? As you are the ITER project is very complex. All the countries involved it may be very difficult. I'm not sure.
Okay, so as in a way, of course, this has impact in the project like everywhere in the world. The impact, I have to say, has been the timing of the start of the pandemic was not too bad for us, in the sense that, as I've just seen, if I go back, you see that many of the components that we receive started to be received in spring last year. So actually, it was not so bad in that sense, because we have now received all the components. If I go here, you for instance see for instance, the vacuum vessel we received in July, the coils we receive in June, the toroidal field coils we receive in spring. So we were, I think, fortunate that the start of the pandemic arrived when most of the components were already, the components that we need to start machine assembly were already fabricated. So they were either finishing in the factory, on a ship coming to Europe, etc. So the impact on the start of machine assembly has not been very large because of this. Of course, manufacturing has slowed down, and this is why I said that it will probably have some impact of a few months. This we don't know yet, because, of course, the pandemic is not finished. But one thing I can say is that, and I will show this because for us this was actually very important, there has been quite a lot of emphasis in minimizing the impact to ITER by the ITER members. So there have been two things which, in my opinion, have been very important. One is internal organization. internal organization, so the ITER director who is here and the management decided to optimize the number of people that are at the ITER site, so that through all times we have the people on site that had to really be there to do the construction. This allowed to keep the machine construction on schedule and minimizing the impact on the pandemic to the ITER staff and the contractors. So this has been quite effective, and we have, I think, got a rather optimized system by which we share on-site work and remote work routinely since the beginning of the pandemic. Another thing which you can see here, which at the beginning was a problem for many people, but for us was less, was the fact that for protection of people, masks, etc., during the spring last year, it was very difficult to get. And this had a big impact. You can actually see that the people at the beginning were not wearing masks at ITER. So, and here we have a big help from our colleagues and partners in the Oriental countries, which send that very large set of masks. So actually, it is I would say, it doesn't look like a major thing, but at the time where it was impossible to find protective equipment in Europe, this was a big help, and actually was noticed in one of the ITER news lines. So I think in general there has been a lot of effort from everybody internally in the ITER organization, but also the companies that work for us, the institute that work for us, to minimize the impact on the ITER project. And you can see that even with the pandemic, we got a lot of deliveries. Some of them are coming now, so there is a lot of effort to try to minimize the impact. But until the pandemic is finished, it's very difficult to quantify, to be fair.
Of course. It's really great to see all these countries collaborating together, really. And what are the future landmarks of the ITER project? Are there any dates we should be looking forward to, or can you make us brief?
So I will provide this a high-level summary. As I said, this is where we are today, and this is where we want to go to demonstrate the first plasma. We will basically test all the components of the Tokamak reactor for the first time, the core components of the vacuum vessel, cryostat, coils, vacuum systems, etc. This is, as I said, scheduled for December 2025, after 1 year more or less of tests. So the big steps, the first one is to complete the first vacuum vessel sector with the TF coils, the one I showed. This is planned for autumn this year, and then we will go in series. Then we will install the next one, and then basically put the coils that we have already, as I said, on the Tokamak pit, and build the machine together. So the detailed plan I can show here. This is the detailed plan where you see here is where the vacuum vessel sectors arrive, how they are, the various coils arrive, all the steps. As I said, the plan, as you can see here, was to put this sector in the middle of the year in the pit. So in the Tokamak pit, this is now in the autumn. So this is one of the impacts of the COVID. So things are a bit slower, but we are talking of months. And the plan is, as you can see here, by the end of 2024, as I mentioned, maybe now sometime in early 2025, to cross the top of the cryostat lead which I showed. And then we start with integrated commissioning to test everything, and this will take a year. So at the moment, we don't know exactly when we will do the demonstration for first plasma, but it will be sometime towards the end of 2025, the middle of 2026, something like that. So for me, the most important steps are, first, the completion of the first sector with the toroidal field coils and the location on site, and then the next one. Because when we do this, when we weld these two sectors, these are the first two, and then we know we have done 2 out of 9 sectors, you can see here, but also we have done the alignment of all the components relative to each other, and I think this is a very big step. So we expect to do this, as I said, to lower the first sector at the end of in the autumn of this year, and to weld the next one sometime next year. So I think this to me, we saw we can do this with a high precision, sometime next year, middle of next year or something like that. It will be a big step. But we have, as you can see, from now to the end of 2024, early 2025, every month there is something.
Yes.
Something happening. So we have a lot of new new events, and very challenging from the engineering point of view, of course. And also I am from the physics side. So one of the things we have to, for instance, evaluate is when we put these sectors on site and we align everything, whether this is good enough or we have to put more effort to realign, because the symmetry of the magnetic field is very important to get the fusion performance. So this is something where engineering and physics actually iterate quite a lot. We have to get from the physics side and the engineering side the perfect machine configuration so that we are sure we will get our goals. Then after 2025, then we start the scientific exploitation of ITER. So as I said, this is first plasma. So we will have about 1 year before first plasma to check that everything is working properly. And then we have several operational phases in which we installed all these components, these in-vessel components, all these heating systems, which I mentioned before, in a phased way. And this at 1 decade process until we get to 2035, where we'll demonstrate DT operations. So here there are installation, checking of things, installation of more components, and finally the start of the demonstration of fusion power production. And this is what we call, from first plasma onwards, this is what we call the ITER research plan, which is actually the responsibility of our division. And this we have developed. This is a layout of the research plan, what we do in every of these phase. And at the beginning, as I said, we will not use the deuterium and the tritium for which produce fusion, but we will use hydrogen and helium gases. So we will not produce fusions. And this is the plan until the end of 2025, where we start fusion power operation, and these are the milestones and what we are going to do. And this is a document which is publicly available, is 400 pages. It gives the ITER operation for the whole lifetime, but in detail until 2041. So you can see that this is a project that is not, it's a project of a large time scale, is complicated. We know it is complicated, and this is why we have done a quite detailed plan of what we have to do and which systems have to be available.
Thank you, Alberto. I don't know if you want to add anything.
No, as I said, to me, I've been working. Let's say I started to be related to the ITER project in 1994. When I was nominated by the European Union to serve as one of the experts to provide input to the design. So you can see we are now 2021, so 25 years have happened. And during this year, we have worked a lot on how actually the details, for instance, of this plan. Many of all the plasma conditions which are considered here, we have a lot of research in the ITER members, because there are fusion facilities much smaller than ITER that support us. So many of these details are done on the basis of experiments that people have done over many tens of years to support ITER. And for me personally, to see after all these years of planning, working on the design, to plan how the machine is going to operate, to see the components finally arriving and that the machine is being materialized this year for us for many people have been very special, because we have been working on this, on CAD designs over the year. But now you see the components arriving, they are there, and you can start thinking of more practical things. So it is a bit of a pity that because of the COVID, we could not celebrate it more properly. But these components have taken tens of years to fabricate, because to the fabrication of some components, the plants to fabricate them did not exist. So you have to build first the plant, then the component. It's a long. So when people say, fusion takes long, it takes long because, for instance, the fabrication of the toroidal field coil cable have to be increased. The production worldwide have to increase by many thousands to get to this ITER coil. So this process is long because the things are technologically very challenging, and it takes this is not like manufacturing a car. This is first of a kind, and actually the plant to fabricate doesn't exist. So you have to build the plant and then fabricate, test it. We have a lot of tests, as you can see. So it is a long process, but I think so far we have not found any major issues. So we are quite confident that the project will be successful.
I hope so. I think it's an amazing project that will change humankind forever. So I hope you are successful, of course. Yeah.
Thank you very much, Alberto, for
Okay,
joining
thank you.
us, and see you next time. Thank you.
Okay, goodbye. Goodbye.
Bye.